Recording now. All righty. All right, there we go.
Ready for me to go?
Yes.
Okay. Here we go. Okay, well, welcome to the Science Fair Data Handling series. I hope that you watched video 1 and 2 that were in the library, but we are going to have a quick review on some of it because the topics are so important. And we'll just start with the review of episode 1, where we talked about that your science project is a story that's told through data, and our inquiry project is used to validate a hypothesis or to validate that our project, and in engineering design, to validate that our project meets its requirements. So we're going to start with the math in science fairs is darts. So if you were to throw a bunch of darts at a board, then you could say that this smattering is relatively accurate, because this is a definition of accuracy, because they're all relatively close to the center, your desired value, right? This, on the other hand, is precise. It's not accurate because we didn't get the our desired value, but we did get a repeatable result. So that's called precision, okay? So if you wanted to have a bunch of, center bullseyes, then it would be called precise and accurate because you can get the same result repeatedly, and it is the desired result. So what does that mean? The most common way to describe data when you're talking about science fair is that the central tendency and statistical variation. So let's talk about what that means. Central tendency is a way of finding the center of your data using things like the mean, the median, and the mode. And this is kind of a review, so I'm going kind of fast, but it's important that you know this before we move on. So the mean is the average of the data, the sum divided by the number of values. The median is if you have a group of values and you place them in order, the number in the center is the median. And the mode would be the number that occurs most often in your data set. For example, if we had this as our data set, 3.1, that was our value, say that we threw our darts and we were very precise, but we weren't very accurate, and we made numbers out of it, 1, 2, 3. Then our median would be 3.7 because it is the center number, right? 9 is the one in the center in order. Our data set, we have 2 3.7s, so our mode is also 3.7. And our average, if you take the average or the mean, is 3.6. Okay? So variation, so there's the center of your data, right? Variation is a way of describing the span of your data. Are they close, or is it precise data, or are they very far apart from each other? So how we represent variation in our data, right? So if we have all of them that are very accurate, we would have a bell curve that's very narrow. And if they were kind of spread apart, then your bell curve would be more wide. In variation, we're describing how far away the points are from the center of the data, right? So the center of our data, we figured that out, is 3.6. And so all the other points, right, 3.1 is farther away from 3.6 than 3.3 is, or than 3.7 is, right? So these are distances from the center of your data when you're looking at a data set, okay? So this is how we describe variation. Now there's a term called standard deviation, and what that is how much that 2/3 of your data will be in the center, right? So when you have a bell curve, you're pretty familiar with bell curves, right? Grades or bell curves. Height is bell curves, right? The average person's height, and there are some people that are really tall and some people that are really short. But standard deviation is frequently used as a measure of the variation of your data, how wide it's spread, right? And I'll show you some numbers in just a minute. So for example, and this is again a review from slide deck number 1. So we're going kind of fast, but if you have, these are series of data. So the first one, every number in your series of data, your data set, is 8. So your mean is 8, your median mode is 8, right? Everything's going to be 8. And your variation is going to be 0. Standard deviation 0. There's no variation. It's all the same number, right? And so now you can see if I said, okay, a third of my numbers are going to be 7, a third are 8, a third are 9. So you can see my numbers, my mean, median, mode are still 8, right? I have minimum, maximum, and my standard deviation is 0.8. So it means that I have a bigger spread of data. And so you can continue down. Let's look at series 5, where I have, you know, a whole bunch of numbers from 0 to 16 in there, right? And you can see that my deviation is 5. It's a measure of how spread apart my data is, right? No spread at all, higher spread, right? And so then there's other interesting things to think about where your data, if is not 8 isn't the center of your data, isn't the median and the mode, right? Even though you have numbers from 0 to 16, right? So what is that? Well, that is skew. So let's talk about skew, okay? So here's the curve that we were talking about. The center of your data is your mean, right? And then you're talking about the span of your data. And you're saying, and of course, that's a way of measuring accuracy or precision in your data, right? Everything's real close to the same number or kind of far apart. So these numbers are, and one of the things, if you go back to this, if you go back to watch episode 1, we hop into Excel and play with Excel and show you how to create all this data. So go look at that for an easy way of doing that. Now, one of the things that we want to talk about in a science fair project is if you are changing your independent variable and you see a change.
Sheila, we lost your audio. I think you just came back on. Try again.
Okay, can you hear me now?
Yes, I can.
Okay, good. So let me go back. What's the last thing you heard?
You started talking about a right and left skew.
Skew. Okay. So when you have a bell curve that looks, you know, like this, we call this the standard bell curve. That means your distribution is random. It means there isn't anything unique in your data.
You need to reshare your video.
Oh, that's right. Okay. Thank you.
Certainly.
Okay. Got that?
There we go.
Oops. Okay. Are we set? We got
Yes.
the visuals and the audios. We'll keep going. Thank you, Michelle. Okay, so when you have a curve like this, just a standard bell curve, that means it's random. And there's no cause in there. It's kind of everything is just random, like an average size of height of people, speed of people running, right? There's most people have an average speed, and then there's those that are really fast and those that are not, right? So this is kind of a random. And when you have one like this, where your median and mode isn't your center, right? And your curve looks like this, that means there's cause. So what does that mean? Let's talk about that. So a normal distribution is the bell curve, right? So let's say, for example, you collect the height of a bunch of high school kids, just randomly select them. The result would likely be a bell curve, right? There'd be those that are kind of in the center, and then, and then there'd be those that are very tall and those that are not so tall, right? The shorter ones, right? This is called a random bell curve. It's called normal, right? So let's look at, for example, a bell curve of a basketball team, right? So you can see that there's a whole lot of tall ones and maybe one short one, some really fast guard or something like that that can get, but this is not a normal curve, right? It doesn't have the nice bell-shaped curve to it like we did in the last one, no bell shape, right? This is called a skewed curve, right? And what that means is it's not normal. That means there's a reason that it's not normal. And the reason that it's not normal is because basketball coaches pick tall people to be on their team, right? So that's called cause, right? So that is, again, the non-normal distribution. Okay, so what does that mean when it comes to trying to validate your hypothesis? Did you validate your hypothesis, or that was the review of episode 1, here we are at episode 2. Or did you verify your engineering design? So what is statistical significance? So let's quickly review your data now that we've kind of reviewed episode 1. We'll take some time to review data. Did you collect enough data, right? Is there enough data there to make, to do statistics? Is it complete? The data must be summarized so the conclusions about the performance of an engineering design or the proof of a hypothesis can be made, right? So just like I said at the very beginning, your science fair project is really a story of data. So let's talk about the types of data that you probably collected for your project. So there is quantitative variables, right, which is a measured quantity, like height or time or temperature, for which you can use and have meaningful arithmetic operations and have average, mean, median, mode, and that makes sense, okay? There's categorical data, which is assigned a number, which can be assigned a number to represent a category, but you're not able to use it for statistics. Like category 1 is girls and category 2 is boys, and there's no such thing as a 1.5, right? Or a 2.5, right? Because so category variables is you cannot do statistics on, but there's other things you can use, and we'll talk about that in a minute. For categorical variables, you can choose bar graphs or pie charts, right? And for time data, of course, there's time plots, and we'll talk about that in a minute. There's other kind of data that perhaps you didn't have a scale for. So, for example, if it's an engineering design, you can use people's opinions, 1 through 5, right? So a 4.2 is a good number in a rating, right? But it's not really something that you're measuring. It's a scale that you've created. Another scale that you can create, I had a daughter who did a lot of projects with Petri dishes and how to measure growth in a Petri dish, right? And so she would put a little, with a light underneath the Petri dish and a graph paper, right, with squares. You can count the number of squares that have growth above it, right? So then you can create, of course, quantitative data from something that is difficult to measure, which is growth in a Petri dish. And if you have a project like that and we have more questions about it, you're welcome to contact the library and get in touch with me or another mentor to help you talk through that. So getting back to statistical significance, okay, means that changing the independent variable has resulted in a change in the dependent variable from the normal behavior, right? So, of course, in the data that you're using in an inquiry design is comparing the dependent variable with the control, and the design, you're comparing your design data with the baseline, right? So quite often when you're trying to improve a engineering design, you're saying, I can make it faster, right? And so you would compare the data that you collected with the original design and then with your design. So statistically significant means that changing the independent variable results in a change in the dependent variable that is not normal. We just said that. Okay. In an engineering design, that means that you have proved that you've made an improvement in your design, right? Otherwise, you'll need to validate your requirements if you don't start with the original design or a baseline. You'll just need to prove that you created or met your requirements. So one other thing to think about is called correlation, right? So that's means that the independent variable that you're changing is a strong cause or a weak cause of your dependent variable. So for example, if you were to graph your data like this, right? This means with the, you have your data that you, independent variable across here, dependent variable across here at y-axis. If you can draw a line through it, then that's called a strong positive correlation. If it has a negative slope, right? If it goes down, then that's called a strong negative correlation, right? If it's like this, where you can kind of draw a line through it, that's called a correlation, but it's weak, right? And it's still a correlation, right? So let's do some math on that, right? So there's a thing called statistical significance that can measure the cause and effect. The t-test is a process that compares data sets, and the p-value is the measure of significance, just like pounds is a measure of weight, right? The p-value is a measure of the t-test. The smaller the p-value, the stronger the statistical significance, right? And a p-value less than 0.5 indicates that the statistical significance is small enough to prove a hypothesis. So you could say that I validated my hypothesis because my p-value is less than 0.5. Okay, so let's look at let's look at that. So here I got Excel coming up here. Let's go to Excel. Let's go to Excel. Okay. So, oops, hang on. Trying to move my Excel here. There you go. Okay, so say I have a science fair experiment where I'm saying the temperature of water, right? So if I drop, let's say, ink in a dish of water with different temperatures, then I'm saying that it will disperse throughout the glass of water faster if the water's warmer, right? And so my hypothesis would be that if I increase the temperature of the water that I'm dropping oil or ink into, it will disperse faster if the temperature of the water is warmer, because particles move faster when they're warm. Right? So here I have just some data. So here I'm saying this is temperature versus time, 3 drops. So say I have water at 40 degrees, right? And I'm going to drop 3 drops of say blue food coloring, right? And I'm going to sit here and time the amount of time it takes for it to just, instead of just be drops in the water, it'll just be a whole glass of blue water if I drop blue ink, right? So it'll disperse and mix. And at 40 degrees, it took 150 seconds. Okay? And at 60 degrees, it took less time, right? And at 180, it took even less time. At 100 degrees, right? And when I got to 140, it dispersed quickly, very quickly, especially considering how much time it took to hear, right? So I have this, and I can look at this data and I can say, this looks like if I change the temperature of water, that my ink will disperse. But it's nice to be able to say that statistically, right? So this is what we do and we go to, in order to go to our t-test, we go to formulas, insert a function, right? And then you can just type t-test up here, right? Type t-test and hit go. And it'll show up down here, and then you turn it on. And here's what it'll say. It'll say, okay, I need your control data. I'm like, okay, here's my control data, 40 degrees, right? It says, what's the temperature? And then your one where you've changed the temperature of water. So I'll go select those. That's 2, okay? And then just so you know, put 2 here because we're using data where we're creating 2 tails, right? A random 2 tails. And then here we'll also put a 2. So put 2 and 2, and then hit OK. Okay. So this is, just like here, the p-value between 40 and 60. Notice that it's very small. So if you aren't familiar with the E-1, E minus number, that means this is actually a point and then 7 zeros before you put the 7 down, right? So eight decimal points, right? So, so say I go and do that for all of these, right? And these are the numbers that I would get if I go and do it for between 40 and 80, between 40 and 100, 40 and 140, right? You can see that it increases, the negative number decreases, so it gets smaller and smaller, right? So that means that there's cause, right? Because this is, what was the rule? Is if it's less than 0.5. So this number is less than 0.5, right? So if I go and round it to, if I go and say, this is actually a number and I only want to see 2 decimal places, it would go to 0, right? Because it's very, very small. It's 0.00000007. So that means that this is statistically significant data, that I could change how quickly the food coloring would disperse in the water by changing the temperature of the water. Okay, so I proved my hypothesis. Now let's do one where I say, okay, I want to compare, I want to see what it looks like if I put different numbers of drops in the water, but I don't change the temperature, right? So here's one where I keep my temperature constant, and I say, okay, here's with 3 drops of water. So it's obviously at 80 degrees, right? That's how long it took. And if I put 4 drops of water, it took about the same. And if I put in 5 drops of water, 5 drops of food coloring, it's again about the same. So here, when I did the p-test value, right, I just went up. Remember, I just went to formulas, insert function, and now since I've done it once before, t-test is down here, just like all the other ones that we've been working on, standard deviation, mode, median, average, right? Okay, so I'm going to go get my array 1, my array 2. I'm going to put in the number 2 for both of these. You just have to take my word for it. And hit OK. And see that number? It's 0.9. What was the rule about statistical significance? That if it's less than 0.5, then that means what you've changed is significant, right? So changing the number of drops of food coloring didn't change how fast it would disperse in the water, but changing the temperature of the water, right? So now you know how to create your statistics, your significance of your data. Let's go back to our presentation and do a quick review of episode 2, right? So that was kind of episode 1, and then a little bit more about Skew in your data. Episode 2 was a little more Excel math and choosing your graph, and choosing the graph that you use to highlight your data, right? So so if you go into you know, we did a bunch of science or a bunch of graphs in episode 2. So go back there and see about all the different kinds of graphs that you can make with your data. Okay. But what we're about now is to figure out how to what graphs you want to use for your data. Okay. So you can use a histogram, which is really a bar graph for quantitative data, right? If you wanted to show that you had cause in your data, which is always very good. The scatter plot is to use statistical techniques when you have 2 variables, like you're changing, you know, the temperature of your water and the amount of time it takes to disperse it in a glass of water, right? Or temperature of water, amount of time it takes to disperse the food coloring. Oops, wrong way. There's other things you can do to show your data. Just if you wanted to talk a little bit about your averages. This is kind of fancy math. If you wanted to show, what your outliers and ranges are, that's an interesting way to do it. You'll probably choose histogram, scatter plot, or a line graph, or then, of course, then there's bar graphs. And this is for when you have quantitative data, right? You see, I don't have numbers down here. I have colors or other things, girls and boys or dogs and cats, right? So if your data down here is categorical, you would use a bar graph. Pie chart is if you wanted to represent a whole, right? So you say, of all the people that I surveyed, 10% of them thought this and 23 of them thought something else, right? So if you wanted to show parts of a whole, the pie chart is really the best way to do that. So here's a summary. So when you have your data that you've collected from your science fair, you need to characterize your data with the things like, we call them the SOCs of your data, which is the spread, the outliers, the center, and the shape, right? So what your data looks like, if it's very accurate, if all of them are pretty much the same, or if they're all pretty much the same, but you had one outlier that you understood or didn't understand because something was different, right? You have to describe your center and the shape of it to show that you have cause, right? So you can characterize your data. Typically, again, the mean is the average and the median is the typical value, right? Average value, typical value. Report the center of the skew, report the variance, and determine the standard deviation, right? Just because that number is, helps to describe whether there was all of it is very repeatable or that it's kind of has a spread. So once the data has indicated statistical significance, the conclusion can be made as to whether the hypothesis has been validated. An analysis can then be used to characterize the relationship between the variables. The measure of the center, the measure of the spread can indicate how results deviate from the mean or vary. Okay, and then you have proven your science fair project. Or if the data shows that there's no significance, then you have proven that they are not related, which is also a valid science fair result. So, so that is the presentation for today. Have any questions? Did you lose me again?
Nope, we gotcha.
Oh, okay.
I don't think we do at this point. So if one more chance for anybody to pipe up or chat in if you've got any more questions. And then I'm going to turn off the recording, and then we can also just chat and see if anybody else has anything. Okay, no more questions, and so I'm going to end the recording.